look at a nice analysis 2 problem. So we have a function. Okay, I guess we'll use the blackboard. So we have a function f.
Give me 1 second because I have to. 1 second, I'm not ready.
From RD to RD.
I'm not ready.
So now, let's say that the limit as the norm of x approaches infinity of f of x is equal to positive infinity, right? So now, what does this mean formally? Well, that means that for all y is greater than 0, there exists x such that if x, the norm of x, is greater than x, or big X, then the norm of f of x is bigger than y. So here's the question. Let's define a set Sy as all x such that f of x is equal to y. And what we're going to do is we're going to show that given, or yeah, we'll do the simplest version. So Sy is compact. Okay.
Can we do it on the board?
No.
I found the marker.
Okay. So compact on RD implies what? Well, this on RD is equivalent to the statement of being closed and bounded. So, what does this mean? Well, Sy is part of some larger set. Well, Sy, okay, let's put it this way. The supremum of Sy exists, and the infimum of Sy also exists. And so we can say that Sy doesn't like extend off to negative infinity, for example. Oh, and also assume f is continuous. Sorry. So now, how can we show that Sy is closed and bounded? Well, first things first, it has to be bounded. Why? Well, let's visualize this in the xy plane. When d is equal to 1, right? So, let's draw so it might cross the same point, and just to make the humps more visible, it might cross the same point many times before moving on. But at some point, it has to move on. As we know, for all y is greater than 0, geez, so let's call this y, there exists an x such that x is the final time f of x is equal to y. Or in other words, when x is greater than big X, f of x is always greater than y. We know that must be true for some x by definition. All right, So that means, and of course, the infimum of x cannot be below, the infimum of sy cannot be, well, anywhere below, so let's write it this way. But we can't exactly say infimum.